Good morning, everyone. My name is Ennio Capria. I am the Deputy Head of Business Development at the ESRF, and I would like to thank you very much for joining us for this first webinar of the series Synchrotron X-rays, Empowering Industrial R&I. Today, we're going to talk about X-ray diffraction imaging, more often called topography, that we organized in collaboration with the Technical Research Institute NanoELEC. Now I have the pleasure to introduce you Ed Mitchell, Head of Business Development of the ESRF, who will be the chair of this webinar, and will give you some hints about how the ESRF engage with the industry, in particular after the recent implementation of our brand new, extremely brilliant source, EBS. Ed, the screen is yours.
The screen, if that's the case and the screen is mine, I have to go slightly festive, and that's the way it is. So I'm Ed Mitchell, I'm Head of Biz Dev at the ESRF. I'm just going to share the screen, hopefully it's going to work out. And just tell you a little bit more about what we're doing at the ESRF for industry. So as Ennio said, this is the fourth webinar in our series looking at how we're working with industry in different techniques. The ESRF, for those, I know there's a lot of you with us today that already know about the ESRF and where we are in Grenoble. We're on a fantastic location in Grenoble in the mountains down in France, in the Alps. We have recently gone through an upgrade. So we're actually shut from something like December 2018 to August 2020. And we spent quite a lot of money on upgrading our storage ring, becoming the extremely brilliant source, which is the world's fourth generation high energy source. And that's actually changed our properties of the X-ray beam that we generate by about 100-fold. We're an international facility funded by 22 countries. You can see the flags across the bottom there. And we have a very strong collaboration with our colleagues at the CEA, CNRS, and other institutes in Grenoble, especially the ILL as well, on the Grenoble Innovation Campus, the giant campus. We have about 10,000 researchers coming to use us every year, and an increasingly significant part of that is actually with industry and technology research and technology infrastructures. And we're very pleased to welcome industry to use our X-ray beam lines. We try to be as open as we can for industry. We know industry wants to work with us in different ways, and we try to accommodate that as much as we can. So industry is more than welcome to apply for public access beam time with us. It's free. The only catch is you must be able to publish your results. The time is a little bit long as well. It's about 6 to 9 months from the application going through peer review. But industry is also more than welcome to come up to us through proprietary services, buying the access, then it's confidential rapid, no need to publish the results. Today, we're really pleased to have about 150 clients spread across the world. Although with the European synchrotron, it's not just European, but we work with countries and companies from around the world. With the recent COVID, a lot of the work, of course, has been mail-in. So we're open to people coming on site when travel is possible with COVID, but a lot of the work recently has been mailing in of samples. We do a lot of tech transfer, and we do a lot of work with collaboration grants, increasingly through Horizon 2020, now Horizon Europe, where we have projects like InnovaXN, which is our co-fund with 40 PhD students jointly with the Institut Larry Langevin, the neutron facility just next door. And each one of those students has an industrial supervisor, with the science being driven by industrial problems. We have other projects like TSMAP, Big Map, focused on batteries with industry, and Leaps Innovation as well, with some other work there with industry in developing advanced instrumentation. Anyway, if you want more information about that, just get in touch with us and we'll be very pleased to help you. So we're going to move on here to Tuni and Jose. They're going to tell us about topography and the impact that it has, what you can do with it, and especially as a very modern tool. It's quite an old tool, I think, right, from a long time ago, but actually now with the BM5 facility at the ESRF, very modern and able to do a lot of work on material science. I think we're going to have two parts here. Jose is going to introduce us to the science of topography, how it works and what it can do, and Tuni is going to take us through some of the parameters and specifications of our BM05 beamline. Later on next year, the end of this year now, right, we've got 2 further webinars coming up, so keep an eye out for high-speed radiography. It'll be probably in about February next year, and we'll also introduce you to the Tomata Innov, which is a program where we help SMEs have access, small and medium enterprises have access to the ESRF with European sponsored support. Anyway, over to, I think, Jose first to tell us more about X-ray Bragg diffraction imaging, which is a very special tool to visualize and characterize crystal defects. Jose, over to you.
Thank you very much. Yes, so well, thank you, everybody. So I'll tell you about X-ray Bragg diffraction imaging, historically called topography, at the ESRF, and I'll show you that this is a unique tool to visualize and characterize defecting crystals. So The plan of the talk is crystal defects, Bragg diffraction imaging, images of the defects, the two techniques, wide beam topography, which is simple and fast, and working curve imaging, actually quantitative. And after that, Tuni will tell you about technical aspects, scientific support, and who can benefit from the use of these techniques. So let's start with just saying that solid state material is mostly crystalline, that is, has a three-dimensional ordered arrangement of atoms. Most of the solid state materials are polycrystals, that is, regions have different orientations, but we are concerned here with single crystals. And that is important. Single crystals are important for both fundamental science and applications. Of course, silicon is the most used one and produced one, but you have also diamond, silicon carbide, cadmium zinc telluride, sapphire, and so on. And so, well, crystals, most of the real crystals are not perfect and exhibit defects. That is, we sketched here a perfect crystal where all the atoms are well arranged, and well, one very common defect is here, it's a vacancy, and this is all crystals have vacancies because this is thermodynamically stable. But you have a lot of other defects which are not stable but exist, like precipitates, which distort the lattice all around, or like dislocations, which are linear defects like that, which correspond to glides in the crystal. And in addition, you have planar defects, subgrain boundaries, twin stacking force, gross striations, and so on. Many of these defects are detrimental for crystal applications, and so it's very important to locate and characterize these defects. Bragg diffraction imaging is a very good technique to characterize these defects. It's based on X-ray diffraction by crystals, and X-rays are Bragg diffracted by a family of crystalline lattice planes when Bragg's law 2D sinus theta equal lambda is fulfilled, where d is the distance between reflecting planes, theta the angle beam between the beam and the reflecting planes, and lambda is the wavelength of the X-rays. Well, if your crystal is inhomogeneous, Bragg diffraction provides information in direct space, and that is because the diffracted intensity and direction of the beam, diffracted beam, can highly vary as a function of the crystalline quality. I show here a curve for no absorption, without absorption, and this curve represents the integrated diffracted intensity as a function of the distortion of the sample. And you see that there is a minimum for the perfect crystal with no distortion, and that goes up for distorted crystals. That is, for in the low absorption case, the regions that display the highest diffracted intensity are the more distorted ones. It is therefore possible to identify distorted areas within a perfect crystal matrix because they diffract differently. At the end of the 50s, there was a tremendous improvement of the quality of silicon produced for microelectronics. Since that moment, transmission electron microscopy was the best technique to look at the dislocations into silicon. But when you had only a few dislocations per square centimeter, well, the electron microscopy was not anymore adapted. So how to characterize these crystals? Well, X-ray diffraction topography was implemented by Andrew Lang and went into practical use to characterize mainly the semiconductor crystals, but after that extended to all kinds of crystals. What is Bragg diffraction imaging X-ray topography? Let's assume you have an extended and homogeneous beam, poly or monochromatic, and you have a sample there. Of course, you have a transmitted beam, which can give you a radiograph, but if your sample is a crystal, And if you turn your crystal to have to be in Bragg position, that is fulfilling the Bragg's law, well, you have a diffracted beam you can record into a detector, and the intensity recorded in that detector is more or less uniform if your sample is homogeneous. But if your sample has a defect, you have contrast into your recorded image, and from this contrast, you can go back to the defect you have in your crystal. An example is first example is the one of inclusions and dislocations in a silicon carbide crystals. Silicon crystals of silicon carbide are grown industrially for high power electronic applications. And that is an image you see here is 500 microns, and you see a lot of lines and small points. The lines are dislocations, the small points are inclusions. Why do you see that? You see that because a defect is associated with a distortion gradient, that is a region that differs from the perfect crystal matrix, and that diffracts differently from this matrix. So you see this region around the defect which is distorted. And so that means the image widths correspond to this region and is in the micrometer range, even if the defect is very small. Let's look at other defects with an image of a flux ground crystal of gallium-doped yttrium aluminum garnet produced for applications. You can see a lot of things there. For instance, dislocations, which are these lines like before, but also growth sectors, which correspond to the different facets growing from the seed during the growing process, and also growth striations, which are there, which correspond to fluctuations into the growth temperature or composition fluctuations. You can also see magnetic domains and even an inception of a crack with a beautiful contest here. You could say this crystal is awful, is full of defects. Actually, it's a very good crystal because the technique we use is tremendously sensitive. That is, growth striations, which appear very clearly, only correspond to a variation of lattice parameter delta D over D of the order of 10⁻⁴. The growth sectors have different orientations in the 10⁻⁵, 10⁻⁶ radians. And the magnetostriction giving this faint contrast of the domains is of the order of 10⁻⁶, 10⁻⁷. So this is a very sensitive technique. Let's go to the comparison between synchrotron radiation and X-ray laboratory sources. This image of silicon carbide was done at BM5 at the ESRF. The exposure time was half a second. This one was done on a Bragg rotating anode, and the exposure time was 2 hours. But this is not the only difference between laboratory and synchrotron. You'll see that there are a lot of things which are just not feasible at the lab, and where you have to go to the synchrotron. You have two versions of Bragg diffraction imaging at the synchrotron. One is very simple, it's called wide beam topography, and the other one is double crystal topography using a monochromatic beam. Well, let's start with wide beam diffraction imaging. In wide beam diffraction imaging, you set the sample to the polychromatic beam, and each family of reflecting planes in the crystal will find a lambda that fulfills the Bragg law. So you have many simultaneous Bragg spots you can record on your detector. And the detector needs to be big and also have a good resolution. And presently, the only detector that fulfills these requirements is X-ray film. So for this technique, we still use X-ray film. The Bragg spots can be indexed. The shape of these spots and the contrast inside is associated with distortion and defects. Well, this is a very fast technique. The exposure time is of the order of 1 second, and the total recording, including the film development, takes a few minutes. you can say that this is a kind of Laue technique with an extended and parallel beam. Wide beam topography is on a topograph gives the local value of the diffracted intensity and also the local direction of the diffracted intensity. This is the image obtained with wide beam topography of a circularly shaped platelet of iron 3% silicon crystal. And you see that the shape is not circular anymore, and you have a lot of holes and also black lines. This is what is called the orientation contrast and correspond to the fact that you have a lot of subgrain boundaries and subgrains into the crystal. That is, regions having slightly different orientations and having in this way for different angles between the reflecting planes and the incoming beam. And so you have diffracted beams which can either diverge or superimpose. When they diverge, you have a white image, and when they superimpose, you have black images. So this is orientation contrast, and you can, from that, calculate the misorientation between the subgrains. On the other hand, when you do wide beam topography, you record a lot of spots at the same time, and on some of the spots you see the dislocations, and on others you don't see them. And that is because the dislocation distort the lattice, but not in a uniform way. That is, when you consider these planes which are there, they are distorted by the presence of the dislocation. But when you consider the horizontal planes which are there, they remain parallel to each other and they are not distorted by the dislocation. So when you use these planes to produce the image, you perfectly see the dislocations. And when you use these planes, you don't see the dislocation. And that means that you not only see the defects and locate the defects, but you can also characterize the defects through the distortion they induce into the different lattice planes of the crystal. Well, let's compare X-ray Bragg imaging with transmission electron microscopy. The spatial resolution is in the micrometer range, and of course in the nanometer for transmission electron microscopy, you cannot compete, but the field of view is millimeters to many centimeters, and is only about 1 micron in transmission electron microscopy. And the angular sensitivity is a lot better for X-ray topography. You can see 10⁻³ to 10⁻⁷ radians when you are limited to 10⁻² to 10⁻³ in transmission electron microscopy. The defect density you can look at is up to 10⁵ dislocations per square centimeter or centimeter per cubic centimeter, and that is 10⁴ to 10⁻⁻ for transmission electron microscopy. The sample size, you can look at large samples with X-ray topography, for instance, 300 millimeter silicon wafers, and you have small samples in transmission electron microscopy. It's non-destructive, X-ray topography is non-destructive. Of course, transmission electron microscopy is destructive. Let's talk about another technique we use all the time, and is the, correspond to the fact that we have a beautiful lateral resolution in the micrometer range, but in the depths, around the depths, as you project 3 dimensions on 2 dimensions, you have a low resolution. You can recover the depth resolution by reducing the investigated volume, like that, and by having a narrow beam, say 10 micrometers, and you look in this case to as a first approximation, to a kind of virtual slice. And for instance, for an ice crystal, where we looked at several sections like that, the sections appear here, and you see a lot of small points into the section. These small points are individual dislocations which produce punctual image, which correspond to the intersection of the dislocation line with the investigated virtual slice. So you have, in addition, depth resolution by using this technique. But sometimes wide beam topography is not sufficient and a more accurate and quantitative technique is required. So we have a monochromatic beam, and so we need monochromatic beam topography. And in this case, we have to rotate the sample to the Bragg diffraction position to d sinus theta equal lambda. If we record the diffracted beam on a pixelated detector, we can have on each of the pixels a working curve corresponding to a small volume in the crystal. So this is what we call working curve imaging. As we have 248 and by 248 pixels on the detector, we have to do a kind of compromise between field of view and spatial resolution. For instance, if your pixel is 1 micrometer, you have about 2 millimeters by 2 millimeters of field of view. And if you want to have a bigger field of view, you have to have a lower pixel size. So that goes to working curve imaging. When recording a series of images laid to say 200 to 500 along the working curve, which is the diffraction curve, we can exploit all the raw images, including the ones at the tail of the working curve. These are the weak beam images, which show in an enhanced way the defects, and each of the pixels of the detector records a working curve. So we have 4 million working curves recorded simultaneously. It is then possible to extract from the pixel working curves a map of the integrated intensity, and with the help of a Gaussian fit, maps of the full width half maximum and peak position. Let's go to the example of a gallium nitride crystal. Well, the integrated intensity map corresponds more or less to what you can have on the laboratory source or on using wide beam. In the integrated intensity map, you have areas with intensity variations associated to the distortion defects. On the full width half maximum map, you have areas that display a higher full width half maximum. We can say that mosaic spread, and this higher full width half maximum correspond to defects, defective regions. And on the peak position map, we have areas with slightly different orientations, in this case, subgains. Let's go more in detail to each of these maps. The full width half maximum map is very interesting because it provides a quantitative information on the distortion within the volume of the sample, diffracting on a given pixel of the detector. And so either, for instance, if you want to have the density of dislocations, you can, if you see the dislocations, count them. But even if you don't see them because they are superimposed one onto the others, there are very simple formulas, the Hirsch formula, which from the full width half maximum and the Burger's vector of the dislocations gives you the local dislocation density. So you can estimate from the full width half maximum map your local density, even if you don't see the dislocations individually. The peak position map characterizes other aspects. For instance, when you have subgrain boundaries, which are regions of the crystal which are slightly rotated one with respect to the other, with a dislocation wall, well, the peak position show you here and there that you have regions where you have different orientations of the crystal, and you can see, if you look at the scale, that the angular variation between the different subgrains, which are clearly seen in this peak position map, are only few arcsecond range. That is, and the same for the section topography. That is, this is a very sensitive technique where you can see very clearly variations of orientations in the arcsecond range. Well, the peak position map also allows to identify the defects, because a given defect is associated with a given context, which constitutes a kind of signature of the defect. Let's look at the example of a dislocation. If you do Bragg diffraction on these planes like that, you see that from one side to the other of the dislocations, you have a variation of orientation, and so a variation of peak position. And that is what you can see on the peak position map, where you have the matrix having a given position, which is gray, and around the dislocation, white and black, that is higher and lower peak position than the matrix. This is a signature of the dislocation. The same if you look at inclusions, precipitates, you have signatures on the integrated intensity, full width half maximum, and peak position. And these inclusions appear as a double lobe like that. And you can identify in this way very easily the inclusions. Another example is the growth of a cadmium zinc telluride. And the people who grew this crystal wished to know if the crystal was as good or worse than the one commercially, that you can commercially buy. And actually the result was that along the growth direction, they had everything. Better in the middle, same as the commercially produced at the beginning of the growth, and worse at the end of the growth. So you can characterize by using these full width half maximum maps in a very easy way the quality of your crystals. And I wish to finish with a slide which has a scientific interest, which shows that when you have a very good crystal and where dynamical theory applies, the fringes resulting from interferences between the propagating X-ray wave fields within the crystals, which are called catofringes for the specialist, appear very clearly, not only in the intensity map, but also in the full width half maximum. You see all these fringes and the peak position. And that was a surprise, but shows the sensitivity of the technique we are using. So the main ideas to retain is that X-ray Bragg diffraction imaging topography, which was implemented at the ESRF and especially at the BM05 beamline, allows characterizing the defect in crystals and crystalline layers with a spatial resolution in the micrometer range and an angular resolution in the microradian range. Several techniques are used for fast and/or accurate studies, and the combination of these non-destructive techniques are a unique added value for the characterization of crystals and deposited layers. Thank you. Tuni will continue.
Good morning, everyone, and thank you, Jose Baruchen, for the very clear introduction of our technique. So I'm Tuni Tangkalis. I'm here now to present to you in the technical point of view, how it works at BM5. So first of all, I would like to give you a short summary of what Jose say about our technique. That first, we can apply our technique for any kind of single crystal, and we have two different kinds of techniques, the wide beam topography and the monochromatic broken curve imaging. Both of them are different and they give not exactly the same information. The wide beam topography gives the qualitative approach for the defect distribution or the global strain or stress. And we can see as well the individual dislocation or dislocation density. When the broken curve imaging gives more quantitative information like the 2D strain mapping or the mosaic or the local distortion of the or the effective misorientation. Normally we start with the wide beam topography first because it's really rapid. Like Julie said, it's just less than 1 second for an image, and we can apply for a large area measure because we have very big beam. Then we can move on to the rocking curve imaging for the selected area when we spend longer measure time, but keep high resolution and more quantitative. Both of the technique we can do in the two mode, either reflection mode or transmission mode. For the reflection mode, we can have the information of either the substrate, either the surface or the core layer on the substrate. And in the transmission mode, we can plot the whole volume of the sample. And we have the other technique also that called the section topography, when we use the very narrow beam of 10 micron. Then this can use for both of the technique, and in that case we can see the slide for along the thickness of the sample. For this one, we can send several beams at the same time. Then you can have the information at different place at the thickness of the sample. And then at PM5, now I can give you some idea how it works. For the sample, it can be a very small sample like a small diamond or a very big sample of 5 kilograms. We can have the wafer or we can have the very big storage, no problem for us. And for the measurement setup, at PM5, we can have wide beam to do wide beam topography or monochromatic beam. We can tune our mono from 6 to 50 Kelvin. For the sample, we have very good resolution. We have 6 rotation axis, and especially the Bragg angular step precision can go down to 10-5 degrees. Can give a very good resolution for the rocking curve imaging, and the detector arm can go for the very large angle of the Bragg angle. Then we can choose either different energy or different reflection, and we have different detector. Then we can change between one to the other one within just less than 1 minute. Also, for the quality of the data, the resolution and the field of view for the wide beam topography, we can have either X-ray film of the 5 micron grain size, and we have the centimeter square of field of view. Or starting from next year, we can have the digital detector, which have the same size but smaller field of view. For rocking curve imaging, we have a very high resolution of the pixel size from 0.65 micron to 10 micron, and the field of view starting from millimeter to 20 millimeter square. And for the data, we can either have the digital image of the X-ray film with a very good solution of the microscope scanning, or for the rocking curve imaging, we can have raw data. It can be the old format of the RSF, it is the EDF1 or the standard H5 at the moment. And for the big data, after the analysis, we can give you individual diffraction image or the width beam imaging the local rocking curve at each distance site, and the map of which have maximum integrated intensity or the peak position in the H5, the EDF, or even the BNG and the BDF format. Also, so now you should have a question that if you have a sample and you want to measure how we can help you, or the procedure that we can start to have the scientific discussion to get the experiment to decide together what is the best choice, the best method, the best technique for your sample. And then the experiment can be mailed in, or you can come like a user to work with us, and we can help you like a local contact during the experiment. Then we can take care of the data treatment and the data analysis as well. We have our own program to do the analysis, and we can help you also for the scientific discussion on the research, because topography is not easy for to see what on the map, and then we can write report, and then we can participate or help for the publication as well. And so for the last slide, I would like to introduce about our team. So we have 3 people in our team for Luca, Tuni, myself, and Jose Paruchen. So we are here. We work for the characterization of the defect and distortion on the crystal for industry, for applied research or the academic research. And in the past up to now, we work with a different material and different purpose for different applications like microelectronic, like photovoltaic, like detector, like resonance. We can work for the people to study on the policing for the surface damage and for the, especially for the program. And we have a list showing here the different kind of material we can do, like gallium nitride, like silicon carbide, like diamond, like silicon, and even the new material like CVT or wax. And especially we can use our technique to characterize the overflow layer on the surface as well. I will stop the presentation here. Thank you for your attention. And if you have any question, we are here to answer.
It's absolutely brilliant. Thank you, Josie and Tuni. We have got some questions. You can, if you want to, Tuni, you can stop sharing the screen. So we've got actually the audience have been answering their own questions, which is very good whilst you've been doing that. And I was remembering during your presentations there the topography we were doing on the ID14 diamonds, like about 20 something years ago. I can't remember, right? The Sumitomo diamonds that we had at the time, and they were very nice diamonds we're using as monochromators on ID14. But anyway, let's have some questions. Jens was asking, but Alan may have answered it, but let's ask the question anyway. Jens was asking, what is the explanation for higher diffraction intensity for defect crystals? Is it because of the energy bandwidth and divergence of the beam? He did not expect this to be true for perfectly monochromatic and parallel beams. Alan, just so you know, Alan responded saying it's called the extinction effect in perfect crystals. Do you guys agree as experts? Josie, you need to unmute yourself. Josie, you need to unmute yourself. Where is it? It's at the bottom of the screen. You've got something that says something like mute stop video participants. You found it? We can't unmute you, unfortunately. If you're having a problem with it, maybe Ennio can run upstairs.
Can you?
There you go. There we
yes,
go. Marvelous.
Okay,
good. Yeah, you're back. God, tell us everything, Josie.
Yes, the 2 persons are right. That is, extinction effects is another way of talking about the fact that perfect crystals diffract less than imperfect one. When you come from very imperfect crystals and you are used to very imperfect crystals, when you by chance you have a perfect one, you say it is extinguished. It gives less intensity. When you start from perfect crystals, you say, well, a perfect crystal defects and the distorted region defect more. But at the end is more or less the same, depending where you come from. And it's true that the curve I showed corresponds to an integrated intensity that is to everything which is under the rocking curve. That is, it's not a parallel beam. It's a parallel beam when you rotate your sample and record all the images around, all the intensities around the rocking curve. And so it's true that the imperfect crystal have a higher integrated intensity than the perfect crystal. If you only look at one position with a very parallel beam, this is not anymore true. So the 2 persons who asked questions are right.
Thank you. Alan continues and is asking some of the advantages of X-ray tomo over TEM are lost. He says when you only gave a 2K by 2K detector, but the main advantage is that you don't have to cut the crystal, which surely changes the defect structure? Question mark, I guess. If you have to chop a crystal in order to prepare it for topography or whatever technique like TEM, you are inducing potentially, I guess, defects into the structure, right, by the process of preparing the sample.
Well, I'm not sure. Of course, you have to be very careful when you position your sample into the diffractometer. That is, the sample has to be there with the less possible constraint. If not, you can induce defects or distortion into your sample, and you look at things you don't want to look at. That is the distortion you induced, and that is not interesting. So you have to be very careful. And of course, it's true that with years of experience, Tuni knows very well now how to handle a sample not to induce this distortion.
Just a side question from me there. You mentioned the kind of the requirement to position the crystal perfectly, like sort of like almost as though it's like weightless. What are the implications for sample environments? I mean, can we do any in situ work? Maybe that's one for Tuni.
Institute work, we did one for silicon that they can probe. At the same time, we watch how the diffraction spots moving during the probe. And we have that kind of work at the moment at ID19.
Okay, cool, thank you. John asks, how are dark field and flat field effect, sorry, I can't speak English. How are dark field and flat field effects corrected in the topographic images?
I think this one is for you, for me, Jose. For our software, we apply the dark field and flat field for each individual image before doing the fitting, and then the Gaussian fit it for each pixel after the corrected. And also, we're not only doing the dark and the flat field, we do as well the normal light with the current and the time scan as well.
Okay. Dennis is asking, does the center of mass of the peak and or higher moments, instead of fitting function, you use, hang on, does the center, maybe it's something like, I don't know whether you can see the questions and answers, Tuni and Jose. I think it might be, does the center of mass, does using the center of the mass of the peak and or higher moments instead of the fitting function improve the contrast? So I guess you've got some kind of peak and you can use the center of the mass of the peak, or you use a fitting function. We
use everything. That is when doing the maps, we do a Gaussian fit of the peak, which is not actually Gaussian, but results to be more or less Gaussian when you convolute with the different resolution, instrumental resolutions. So Gaussian appears to be a very good approximation. We tried others, Gaussian is the best. And of course, the Gaussian fit gives you the full width half maximum, which is used to produce the full width half maximum map, and gives you also the center of mass, which is used for the peak position map.
Okay, I can see Carsten couldn't resist replying to the perfect crystal debate, which is still ongoing there. Alan asks again to Tuni, what detector do you use to obtain 5 micron resolution over 1 by 1 centimeter?
What is the detector? So we use a Marana camera. We have the 11 micron pixel size, and then we have the optic to magnify to 5 micron.
Okay. Yuri asks, he says, thank you for the presentations, guys. And he asks, do you work with backwards radiation?
Do you, sorry?
Do you work with backward radiation? I don't know either. You have to. I mean, I'm just a structural biologist, right? I mean,
maybe backscattered.
Reckon backscattered. If Yuri says yes, backscattered. Well done, Enyo. Thank you.
Most of the work we do is in transmission, but we can do work in reflection, and of course also backscattered if needed. It's not the usual way of work we work, but it's perfectly possible.
That I confirm by the technical aspect that is possible to do at BM5, but we prefer to do in the transmission and reflection because we have more intensity, but that is possible if we really want to do.
Okay, there's a last question from Valerio, who's asking about the exposure time. So what's the kind of minimum exposure time at the peak or rocking curve, and are there limitations in that sort of exposure time? So looking at throughput and what you can do, I guess.
Well, the exposure time in wide beam topography can be as small as a fraction of a second, say a tenth of a second. Usually we are limited by the fast shutter, and so we manage not to have less than 1/10 of a second, because if not, it's not homogeneous, the exposure. So we reduce the beam to not to have less than 1/10 of a second.
Olivier asked, Olivier Barmes, who we know very well, asked, what is the largest practical sample size and on which beam line? And as a supplement question to that, can you stitch images, like in tomography, can you stitch images together to enlarge the field of view?
Yes, we can. Our beam for the wide beam topography, we can open to horizontal 80 millimeter and vertical is 10 millimeter, and then we have the Z, X, and Y to move the sample. And the larger at the moment we did up to now is 120 by 120 millimeter. But then we can move the sample and stick the image for the larger or field of view.
Okay, cool, very nice. Elodie, it's a bit cheeky, Elodie, asking a question, but that's no problem with that. What did you gain with the EBS for the technique of topography? Is there any sort of link to the increased coherence of the beam that we have now with the EBS, or with intensity? Can you go faster? I know there's been a big change on BM5, right? Because you're no longer a bending magnet source.
Yes, we're not in the bending magnet source anymore. We are in undulator, and now with the new setup of BM5, we get 2.5 time of intensity. So our measurement is faster. We have smaller beam than before, but it's not too much smaller. But we get a lot of time when we do the rocking curve, because normally the rocking curve before the EBS we do, it takes us 3 hours to do a rocking curve, and it's now less than an hour for a very, very big rocking curve.
Okay, no, that's super nice. I am out of questions, right? So this is the last chances. I don't see any more coming through. So thank you very much. Oh, hang on, that was just in time. Got a question saying, is it possible to form XRDT measurements by simultaneously irradiating a natural crystal to evaluate the role of structural defects in the changing of properties of a crystal?
It is surely possible to do that.
That's a very concise answer. That's very good. Sorry, Suni.
Yeah, and also that is it's not something really difficult for us. We did many times with for the natural diamond.
Okay, and Valerio came back, which is a very cool question. Would you have enough signal if you used a single pulse of X-rays from the synchrotron? Oh, la 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 la! Even with the EBS?
That was used. Not by our, yes, that was used on ID19 for, was used for to have a real-time recording. So yes, it is possible. It is possible. But of course, you don't have the same resolution and the same statistics as we usually have. But it depends. If what is important is if to have a very short exposure time. Yes, that was done on ID19 2 years ago.
Yeah, they were following a cracking process, right? I think, if I remember correctly, actually watching glass cracking in real time or something. What you should challenge us, Valerio, and get us some samples for some pulse-based topography. I think we're done with the questions. It's coming up to lunchtime. So thank you very much to Tuni and Jose. That was a fantastic insight into what's really is actually quite an elegant and beautiful and simple technique available for every. Oh, hang on. Alan is back. I think that's your fourth or fifth question, Alan. But anyway, is there really no damage with radiation damage? That would be my normal question as a structural biologist. Is there really no damage with such a strong X-ray beam? And we'll make this the last question.
If you have a biological crystal, yes, you have radiation damage. Usually with the metallic or semiconductor crystals, so we have the radiation damage is very, very reduced.
Okay, brilliant. Thank you very much. With that, I wish you a very happy Christmas. I hope you get to see some friends and families and get to do some travel if you're planning to do so. Have a great new year, and we'll hope to see you in some of the webinars in 2022. With that, we hand back to Ennio to close down.
Thank you very much, Ed. Thank you to all the speakers, and thank you everybody for joining us. It was very nice to see so much interest. We have fun, of course. We're very enthusiastic about this station, and specialized station that we built in 2015, and now we are evolving. And I would like also to thank again my colleagues of the Technological Research Institute NanoElect that are very much involved in all these projects around topography. And very nice Christmas time to everybody and end of the year celebration.
Thank you. Bye.
Bye-bye.